Assalamualaikum and hi. Today our experiment is T1, equation of states of ideal gas. With our group member, Intan Maisara, Nur Fatin Balkis and Sharifah Farzana. The objective first, to measure the volume of a column air as a function of its temperature at constant pressure, K-Lattice law. Second, to measure the volume of column of air as a function of its pressure at constant temperature, Boyle's law. Third, to measure the pressure of a column of air as a function of its temperature at constant volume, Amante's law. Last, to determine the expansion coefficient alpha, pressure coefficient beta, and compressibility K of air. The operators of this experiment are gas law operators, temperature pad, thermometer, and immersion thermostat. The procedure for water circulating system. First, the thermostat water bed is filled with distilled water up to the level where the heating coil is fully immersed. Second, the temperature control knob is set to the initial temperature volume room temperature. Third, the main power supply and the thermostat power switch are switched on. The water circulating system is ensured to be working properly. Fourth, the temperature reading is recorded only after the water temperature has stabilized. Measurement of V as a function of P at constant T. First, refer to figure 1, the top of the mercury reservoir in tube B is removed. Second, tube B is raised or lowered until the mercury level in tube A and B are the same. Third, the height L of the air column in tube A and the temperature reading T are recorded. Fourth, tube B is raised to a new height and the difference in height delta H between mercury level in tube A and B is recorded from the scalar readings. Fifth, the new height L of the air column in tube A is recorded. Last, step 4 and 5 are repeated for at least 6 pairs of delta H and L, and all the data are recorded in table 1. Measurement of V as a function of T at constant P. First, the temperature control knob is set to the initial temperature, room temperature. Second, the thermometer reading T is recorded when the temperature has stabilized. Third, the initial air column height L in tube A is recorded. Fourth, step 1 to T are repeated for at least 6 pairs of T and L, and all the data are recorded in table 2. Measurement of P as a function of T at constant V. First, the air column height L is set to a suitable value by varying the position of tube A and the value is recorded. Second, the initial temperature T is recorded when the thermometer reading has stabilized. Third, the initial pressure B is recorded by measuring the difference in height delta H between mercury level in tube A and B from the scalar reading. Fourth, the temperature T of the air is increased using the temperature control knob, and the volume of the air is kept at its initial value by adjusting the height of tube B. Fifth, the new temperature T is recorded when the thermometer reading has stabilized, and the new pressure B is recorded from the height difference delta H between mercury level in tube A and B. Step 4 and 5 are repeated for at least 6 pairs of T and delta H, and all the data are recorded in table 3. Data table 1 for measurement of V as a function of P at constant T. Data table 2 for measurement of V as a function of T at constant P. Data table 3 for measurement of P as a function of T at constant V.
So for the data analysis, we are going to plot following graph: P versus 1 over V, V versus T, P versus T. And we are going to calculate the slope and intercept using the LSM method with their uncertainties. Then we are going to calculate the coefficients. So for the volume and pressure P of the air in coulomb can be calculated by using these equations. So the calculation is repeated for all data. Then the calculated data is tabulated in this table. We have 3 tables here because we are going to plot 3 graphs. Next, this is graph of P versus 1 over V, showing that it is a linear graph. So this is the LSM for graph of P versus 1 over V, and slope and intercept with their uncertainties. Next, graph of V versus T. It also show that it is a linear graph. This is the LSM for the graph. Slope and intercept uncertainties. Graph of P versus T, also showing that it is a linear graph. This is LSM for graph of P versus T and slope and intercept uncertainties. So, we are going to calculate the expansion coefficient. We do obtain that the expansion coefficient is 9.78 times 10 power of negative 4. Comparing it to the standard value, we obtain the percentage error is 47%. It's quite high from the standard value. Then pressure coefficient. Calculated pressure coefficient is 3.92 plus minus 0.03 times by 10 power of negative 3. Comparing it to the standard value, we obtain percentage error is 7%. Then the compressibility coefficient, we do obtain that the coefficient is 0.013 times 10 power of negative 3 per Pascal. The uncertainty is plus minus 9.12 times 10 power of negative 7. Comparing it to the standard value, we obtain percentage error is 22%.
Discussion. In this experiment, 3 types of graph were plotted: pressure versus inverse volume, volume versus temperature, and pressure versus temperature. Each graph shows a linear trend which supports the fundamental gas law. From the pressure versus inverse volume graph, a clear inverse relationship was observed, aligning with Boyle's law, which stated for a fixed temperature, the pressure of a gas increased as its volume decreased. Similarly, the volume versus temperature graph show a direct relationship, supporting Charles' law, while the pressure versus temperature graph verified Gay-Lussac law, which states that the pressure is directly proportional to temperature when volume remains constant. Based on the data collected, the thermal expansion coefficient of air was determined to be 9.78 plus minus 0.49 times 10 to the power of negative 4, which deviated by 47% from the standard value. The pressure coefficient was found to be 3.92 plus minus 0.03 times 10 to the power of negative 3, with a deviation of 7%. The compressibility value calculated was 0.013 times 10 to the power of negative 3 plus minus 9.12 times 10 to the power of negative 7, differing by 22% from the accepted standard. These deviations are relatively minor and can be considered acceptable in the context of experimental work. Possible sources of error include difficulty in obtaining accurate reading due to meniscus alignment, slight fluctuation in water temperature throughout the experiment, and parallax error when measuring pressure using a scale. Overall, the experiment successfully demonstrates the behavior of air as an ideal gas under normal conditions. Next is conclusion. The first one is the graph of volume against temperature is plotted with gradient of 0.1 plus minus 0.02 and y-intercept of 2.25 plus minus 0.07. The second one is the graph of pressure against inverse volume is plotted with gradient of 2.53 plus minus 0.06 times 10 to the power of 3 and y-intercept of 5.4 times plus minus 2.4. The third one is the graph of pressure against temperature is plotted with gradient of 0.38 plus minus 0.03 and y-intercept of 96.8 plus minus 1.2. The last one is the expansion coefficient is 9.78 plus minus 0.49 times 10 to the power of negative 4. The pressure coefficient is 3.92 plus minus 0.03 times 10 to the power of negative 3. And compressibility K of air is 0.013 times 10 to the power of negative 3 plus minus 9.12 times 10 to the power of negative 7. The last one is reference. This is the four reference that I obtained about this experiment, and that's all for my presentation. Thank you.